Hi, thank you for listening. I'm Esty, and I'm going to talk about a joint work with amazing collaborators, Omri Ben-Eliezer, Meir, and Sofya Raskhodnikova. Uri is the one that initiated and pushed this project. From working with him, I can say that he has a deep understanding of mathematical objects, and he is an expert in combining things from different areas, as you can find out in our paper, Property Testing with Online Adversaries. Property testing works in a more general framework of sublinear algorithms. Let me start with a brief introduction about this. We have a randomized algorithm that has query access to the input. You can think about the input as data stored in a server, and the algorithm sends queries to the server about what is in this location, what is in this location, get answered every time. The goal is to produce an approximate answer. And in this area of sublinear algorithms, we want to understand the trade-off between the quality of the approximation and the resources. Usually when you want a better approximation, you need to use more queries or run longer time. In particular, in sublinear algorithms, we want the number of queries to be much smaller than the entire input, and the running time to be sublinear in the input length. In this line of work, we want to investigate what if the access to the input degrades over time. Such situation introduced and modeled formally by Kelman, Raskhodnikova, and Varma. They call it the online erasure resilient model. In such a model, we have on the background, in addition, an adversary with a parameter t, which is called the t online erasure adversary. As before, we have a randomized algorithm with query access to the input. Now, after each query answered, the adversary can intervene and restrict the access or delete some input points. In this animation, t equals 2. After every query, we have 2 erasures. At some point, the algorithm is going to might query an erased point. Then he has no idea what has written there. Usually, the algorithm has no idea what are the eraser location. Motivation for such a model vary. For example, in privacy, you can think about information of a population in a database, and your own data is also there. You realize that someone accessed your data, and now you're going to restrict all the records related to you. There are some other motivations from social networks and navigation apps. And our main question is, how such an adversary affect computational tasks? And Kelman, Raskhodnikova, and Varma showed interesting results about it. There are tasks that require more queries than the standard model without adversary. For example, testing linearity, we'll talk about later. And there are tasks that are even impossible to test in such a model for any t. For example, testing sortedness. In relation to these specific 2 examples, our results are, we show how to test linearity with the optimal many queries, matching the lower bound from the first line here. And for sortedness, we show how to refine the model a little bit, and then we can test it. And our work implies also new optimal testers in the case without adversary, and with the nice property that our testers are simpler than the testers known before. And we have more results, for example, for low degree testing and other properties. So the plan for this talk, we see what is the online erasure resilient model. We next define property testing, and we'll talk in depth about testing linearity. And after that, we'll see our contribution for the online erasure model for property testing and some refinements of the model with our results. So let's talk about the property testing. A property testing is a relaxation of decision problem. In a decision problem, a randomized algorithm has input that comes from a universe of yes inputs and no inputs, where the yes inputs, sometimes called property, sometimes called language, and the no inputs are all those that doesn't have this property, that are not in the language. For an input that comes from the yes, it has to accept with probability at least 2/3. Input that come from the no it has to reject with probability at least 2/3. How efficient can be such an algorithm? So it might be the case that one input from the yes and one input from the no differ in only one location. Now, in order to see this specific location, even a randomized algorithm has to query almost the entire input. And here come a relaxation suggested first by Rubinfeld and Sudan and defined later also by Goldreich 171. Instead of rejecting all the NOR inputs, we require the algorithm to reject only those NOR inputs that are far from all the yes inputs. Here you have a parameter epsilon, usually given to the algorithm for how far. We say that two objects are at distance epsilon if they differ in an epsilon fraction of places. And what about such inputs that are not in the yes class, doesn't have the property, but epsilon close to some input that has this property? We don't care what the algorithm say. It can either accept or reject, that's fine. For example of property that we can test is linearity. Linearity testing was among the first problems to study in this model, and it's considered as a fundamental problem for property testing. And it's played a crucial role for some inapproximability results of NP-hard problems throughout studying. So what is a linearity testing? In our case, we have the input is a function of n input bits to one output bit. We think about a function as a function over f2 with the group operation plus is the XOR, actually plus mod 2. And we say that f is linear if and only if for all two inputs, n input bit x and y, f of x plus f of y equals to f of x XOR y. Here the XOR is bitwise XOR. In the property testing, we want to distinguish between linear functions and functions that are epsilon far from all linear functions. Bloom, Luby, and Rubinfeld observed that if a function doesn't satisfy this 3-point equality for all xy, but for most xy, then f is essentially linear in the sense that it's actually close to linear function. And this suggests a simple test. We call it a 3-point checker to find a violation for linearity and reject. Later, Belaret, Komper-Smith, Hastad, Kivi, and Sudan showed stronger soundness, meaning that if f is epsilon far from all linear functions, then this 3-point checker is going to find a violation for linearity with probability at least epsilon. So there is a natural algorithm here. Let's do some animation for this. So we have the algorithm, and it wants to test linearity. So sample x and y, query their values, and now the next query that it's going to ask is x XOR y. Once you have all of this information of fx, fy, and f of x XOR y, it can just ask whether these 3 points forms a violation of linearity and then to reject, and otherwise it accepts. We can see for the completeness that the yes case that all linear functions are always accepted because of the characterization. The epsilon far functions are going to be rejected with probability at least epsilon. This is what proved by Belaret, Komper-Smith, Hastad, Kivi, and Sudan, and the query complexity we see is constant. We can repeat this algorithm 1 by epsilon times to get the rejection probability at least 2/3. What happened now if we try to run the same test, but we have the adversary? Let's try. So we query x, we query y, and our next query is going to be x XOR y. We are not the only ones that know it. Also, the adversary knows this information. So it's going to use its power and restrict our access to x XOR y. When we query x XOR y, we have no information, and we can perform the 3-point checker. How can we overcome the adversary? The idea is to not let the adversary knows what is our next query. And for this, we add more randomness. We create more options for every query. Let's try to do it together. So for example, we can just query, we might try to query many points. And then we call these points a reserve. We query many points much larger than t points. We're not going to use all of these points in order to decide whether the function is linear or far from linear or non-linear. we just query them in order to confuse the adversary, in order for him to not know what is the point that we are going to use next. Now we choose a random point from our reserve and query f of xi, xor, y. If we don't see any erasure and the 3-point checker find a violation, we reject, otherwise we accept. How does this tester look to you? So the linear functions are always accepted because they are not going to satisfy the second condition here. What about the functions that are epsilon far from all linear functions? So by the BLR test and BCHKS analysis, the second condition is going to hold with probability at least epsilon. What about the first condition, about seeing an eraser? So it was noting that after we query Fy, the last point, the adversary knows, it has some idea about our next query. It knows that our next query is going to be of the form fxi xor y from 1xi from our reserve. And he wished to erase all of these L points. But he has the ability to erase at most T points. And now, whatever smart strategy he will use, after he erases T points and we choose a random point, if L is much larger than T, we are going to see an erasure with very small probability. This way we get a rejection probability order of epsilon. And the query complexity is actually the size of our reserve, which is larger than T. Again, we can repeat it 1 by epsilon times to get a rejection probability at least 2/3. This is not the point here. And the question is, do we really need this reserve to be that large? Or can we do better with less points in queried at all? And the answer is yes. And testers for this based on generalizing the BLR 3-point checker to general even K. Just instead of having fx1 plus fx2 and XOR them, we have K points and XOR them. Kelman, Raskhodnikova, and Varma showed a tester of that many queries based on this K point checker. They were the first to prove some soundness for this. Their algorithm is quite involved and used their work investment strategy. Another interesting result that they showed about linearity testing is a lower bound. Any algorithm with the adversary that want to test linearity has to query at least log T data points. What we show a new tester for linearity with query complexity matching their lower bound, and our tester has another property that it is very simple. We know that our tester is optimal in both parameters, the epsilon and log T. The main technical thing that allow us to do it is improving the soundness of the K point checker by a factor of K. And it also proposed naturally another tester which is simple and optimal for the model without adversary. I say that our tester is very simple. Let me show it to you. What our tester does, it sample and query 2K uniform points. This is going to be our reserve. We're not going to use all of them. And now it sample a uniform random subset of size K of indices from 1 to 2K. How many options we have here? Roughly 2 to K. And then it's query the XOR. It rejects as before if we don't see any erasure or the K point checker find a violation. Otherwise, it's accept. Again, it's easy to see that all linear functions, this is algorithm. All linear functions are going to be accepted because they're not going to satisfy the second condition. For the epsilon far inputs, the second condition is going to be satisfied with probability at least K epsilon. This is important. And if we take K large enough, it's going to be a constant. Now, if we choose carefully the value of K and then just use a simple repetition, we get an optimal query complexity. So this is about linearity. Let's see what we are going to talk about our contribution. So we talked about linearity tester, which is optimal for the erasure resilient model. We will discuss a little bit our results for low degree testing, and then we'll show some refinements of the model and sortedness testing for results for such refinements. So for the lower degree testing, what is lower degree testing? We have a function again over F2 with n variables. And the fact about such functions is that any such a function can be written as a unique polynomial over F2. The degree of the polynomial is, as you think about it, the largest monomial with non-zero coefficient. And the question is, we want to distinguish between polynomials that are of degree at most d or functions that are epsilon far from all polynomials of degree at most d. We showed that testing degree d with t erasures per query requires at least log t to the d queries. What we proved is a relation between our question of how many queries needed to a degree d dependency, and I'm not going to talk about it too much. This essentially proved by Kivash and Sudakov, and later by Ido, Ben-Eliezer, Od, and Lovet. It was noting that in a concurrent work, Mintzer and Zeng showed an algorithm that almost matching our lower bound. And we saw this lower bound and said, okay, well, we want to do better. So how can we do better? We showed that in a relaxed version of the model, we can test lower degree with much less queries. So the refinement, we call it batch queries, and it means that the adversary allowed to intervene only after answering a few queries together. You can think about it that there is a server, and instead of asking one query at every interaction, you can ask many queries in every round, and the adversary can do whatever he knows, erase, delete, restrict, only in between interactions. For our algorithm, which works on a non-trivial size of batches, we used local characterization by Kaufman and Sudan. In particular, we defined algebraic testing patterns for local characterization and proved some algebraic structural results for them. I'm not going to go into it, but it's very interesting. So next, I'm going to talk about some refinements of the model. So the model by Kelman, Raskhodnikova, and Varma, they think about integers values of t. We allow any non-negative value of t. And the interesting part is t, which is less than 1. You can think about it intuitively as that at every step, the adversary can erase one entry with probability t. This is not the model exactly that we talk about, but this makes sense. It's similar. And naturally, we can now consider two types of adversary. So the fixed rate adversary must use erasers whenever they are available. Once it has a complete one eraser, it has to use it. For example, if t equals 1/4, it means that the adversary can erase at any 4 queries in the 4th query, and 8th query, and 12th query, and so on. If t is closer to 1, it's less intuitive. Let's say that t is 3/4, then the adversary is not allowed to erase once in every 4 queries. For example, it's not going to erase after the first query, the 5th query, the 9th query, and so on. Another type of adversary is stronger in the sense that it can choose, and it can save the right to erase for a later time in the algorithm. For example, for t equals 1/4, it can do nothing until the 12th round and then erase 3 data points at once. Next, we'll talk about how sortedness testing for all of these various models. So what is sortedness? We have a sequence of n real numbers, and f is sorted if f of x is at most f of y for all x smaller than y, not worth it. And we investigate it for different values of t. So if we start with t equals 1, we have the impossibility result by Kelman, Raskhodnikova, and Varma that they showed it's impossible to test. We extend the result, showing that the budget managing adversary is the stronger one. We cannot test for every t which is larger than epsilon, even if it's just a constant times epsilon larger. For some large constants, it's impossible to test. And here we show a dichotomy around t equals epsilon. For every t which is smaller than epsilon, we can test. And not only that we can test with optimal tester, in the sense that our tester is optimal even in the model without adversary. For the fixed rate adversary, we show that there is a sharp transition at t equals 1. For every t smaller than 1, strictly smaller than 1, but close to 1 as we want, we can test sortedness. And if t is smaller than some constant, let's say at most 0.99, then we even have an optimal tester. For batch sizes, when batch size 2, when the algorithm has a guarantee that it can query pairs of queries together without the adversary erase anything in between them, we show that there is an optimal tester for t even of size n. And here is a big difference between batch size 1 and batch size 2. For 1, we cannot test at all, and for every t, and for 2, we have an optimal efficient tester for even huge values of t. So just to summary what we saw in this talk, we had an optimal tester for linearity in the online erasure model, lower bound for low degree testing. Then we refined the model to allow batch queries, to use fractional rate, erasure rate, budget managing versus fixed rate. And then we show how to test sortedness, and we also have a tester for low degree in batch queries. Some other things that you can find in the paper, there are some results for when the adversary is allowed not only to erase, but to corrupt the data. And then the algorithm doesn't know whether the data corrupted or not. It's the same. So this is a bit more challenging model. And we also have an optimal simple tester for all local properties of sequences, which is a huge class of properties. Let me discuss some open questions. It will be interesting to find the query complexity of low degree testing in the online model. Just recall that we have a lower bound and there is almost matching upper bound. Interesting to see what is it, the complexity exactly. We didn't talk about it, but our tester for linearity works for t, which is at most roughly 2 to n half. And it is interesting whether we can handle larger values of t. Maybe there are some values of t that we cannot handle. Like t is at least epsilon 2 to n is trivial that we cannot handle it, because the adversary can erase all the witnesses at once. But other than that, can we show other properties for this model? For example, authenticity of the hypercube or some properties of graphs. There is another model that was mentioning is the offline erasure model, when the adversary makes all the erasures before the algorithm starts running. And it's known that it is harder than the standard model, but easier than tolerant testing. And the question is where in this picture the online model placed. Thank you for listening.